Today we're going to learn how to take data and put it into ML or AI systems, so machine learning AI systems. To do so, we have to take data that you and I and many other persons can recognize and turn it into something that computers can compute on. And in early machine learning, maybe even early algorithms and computing, we might have a bunch of things that are already in numbers and already in some sort of numeric system. And we might therefore just be like trying to draw a line or recognize a trend or fit all of the points or whatever it is that we're trying to do. And in those cases, sometimes we didn't even need machine learning because the data is already in numbers and maybe it's just a simple algoritm. Or it could be even other ways that we tried to take words we understand, like the number of spam words, and calculate if it's above or below a certain threshold and then mark it. And these are like really simple machine learning, sometimes even not machine learning, but statistical problems or algorithm-based problems. So that's like pretty easy stuff. And that we've been doing for a long time. But what about like if we want to take an image? Like I have this nice piece of art that's on a card. To give credit to the artist, it's scoutededitions.co.uk. And so I have this nice piece of art. Maybe I want to understand what it is. Maybe I want to know what colors it is. Maybe I want to know art like it. Maybe I want to generate art like it. Or it could even be like an image recognition. So what's in this image? So you could also think of a photo and figuring out what's in a photo. Or maybe it's, I have some political text. So maybe it's AFD, which is a party here. Voting is so 1933. So maybe you want to take even text, or you want to take text out of an image, or you want to take text and then you want to do some sort of learning on it. Well, how do you actually do that? The problem is that those relationships are more complicated, obviously, than these earlier ones that we looked at. And one of the ways that we use machine learning to do this is a system of math or an area of math called linear algebra. And linear algebra has been around for a long time. And it's been used for a long time, way before machine learning used it, to take something like a natural system. Let's say this is like fluid dynamics. I'm not an expert in fluid dynamics, so please comment if obviously these equations don't actually map, but we take something like fluid dynamics. We model it into some series of equations or some series of systems. And what linear algebra is really good at is it takes a series of equations that model some sort or represent some sort of dynamic or system, and then it allows you to build things called matrices or other types of linear algebra, kind of like foundational structures. And those allow you to take really complex, here I've represented 3D space, but even, n-dimensional space. You could think of million-dimension space. And when we take these systems and we try to model them in that type of mathematical space and we try to preserve their relationships, we can actually end up creating kind of nonlinear representations and relationships between these sets of numbers. And then we can learn or we can gather information from the relationships between those numbers. So if we do this in a clever way, which many people have done for many years, we can then take things like these images and this text, and we can actually put them into some sort of space, let's think, and try to learn that. So one of the papers that really was a breakthrough in this was AlexNet. And AlexNet was one of the first really deep learning papers where they showed not only deep learning as feasible because they parallelized some of this linear algebra, but also in deep learning, what we have is kind of linear algebra is happening at each of these interfaces between layers. So we call it deep learning because we have many layers of these types of things, and you'll learn more in the next few videos about these systems. But we use the power of linear algebra in deep learning, and that means that we compute a lot of linear algebra types of transformations and other ways of computing things with matrices when we do deep learning, and this happens at a bunch of points. And that's really expensive. So before we learned how to parallelize using something like GPUs, people were like, oh no, we're never going to use that. It's way too expensive. But AlexNet not only showed that it could be parallelized and you could learn using two GPUs alongside one another, but also showed and outperformed a bunch of the other image recognition models at the time. And AlexNet used what we today call CNNs, which weren't new to AlexNet, but it was mainly new the way to put them together that AlexNet did. So that was pretty cool because that showed, okay, deep learning can take the cool power of linear algebra, can take complex input like images, and can do really well at something like, is there a flower in this image, or what's in this image? Yes, no. So that's cool. And that led to people saying, well, how are we going to do this with language? And language is hard because in an image, at least images stored on your computer, we already have kind of the pixel colors. So for each, you could take the number for each pixel and you could take them one after another, and you could try to accentuate changes in pixel color. And there were all these kind of cool things that were working well for computer vision. But what about language? Language, we borrow a lot from linguistics. And so if we look at linguistics and we take something like the words foundation, founding, lost and found, we might use what we call word families or word roots to say the word root here is found, the word root here is found, and that's the same word root here. Okay, so we got word roots from word families. That's what we can learn from linguistics. And when we do NLP, we want to tokenize. So we want to kind of find chunks of words that can help. Again, we want the patterns to exist because linear algebra wants to show us patterns in sets of numbers and their relationships. And so how do we figure out how to represent this in numbers and relationships? Well, maybe breaking them down into these word roots is a good idea. And then these word roots can store information. That's what we hope, right? But when we look at foundation and founding, that's kind of has similar roots, meanings for us. So a foundation is kind of a group working together on a particular idea. When you're founding a thing, you also kind of have that intention. But lost and found is actually kind of a different interpretation of the word found. It holds a different meaning for us. So you can start to see the limits that we had in language for a long time of just trying to take what we know from linguistics and put it into a machine learning model. Well, that all kind of changed when we started using word embeddings. And so word embeddings kind of first surfaced in a paper around word2vec, which you can see the linear algebra origins. It takes a word or a token, which could be a part of a word like you just saw with found, and it maps it to a vector. And this is a structure in linear algebra. And so here we have, again, an example 3D space. And we might have the vector for man and the vector for woman and the vector for king and queen. And what word2vec showed is that it could train a mapping or an embedding, as we would call it today, so that the embedding of man, when we take the distance and direction to king, was actually the same or very close to the distance and direction between woman and queen. So you could say that the relationship in this embedding space of man to the word king was the same or similar to the relationship between woman and queen. Now, the unfortunate truth about word2vec is of course heavily dependent on the training data. So you have to learn all these embedding relationships and learn how, kind of how they work together. But that it worked really, really well for deep learning. So this is kind of the base of a lot of the language models that we use today that are so powerful, like GPT models. But the other unfortunate thing is this also encoded a bunch of other icky stuff. So if you took man and computer programmer, something that I looked at many years ago when these vectors were first released, you actually, when you took it and applied it to woman, you got homemaker. So obviously, as a woman computer programmer, I found this to be like not so great. And there's many other examples of other things that we program into these embeddings that represent the information that we're trying to learn. And that is then learned in a very similar way to AlexNet. We then take these embeddings, kind of similar to how we took the pixels from the images, and we use, again, the power of linear algebra to perform a series of different layers, we called them. And this does a bunch of matrices and other types of linear algebra computation. And this allows us to take, again, those relationships that are encoded in those numbers and try to learn from them. Now, Hamburg Data Protection Authority released a position paper, a discussion paper earlier this year. And they said, oh yeah, these embeddings, it's fine to use personal data with them because these embeddings use tokens. And tokens aren't personal data, so it's totally fine. And as an example, they showed just the GPT example of taking a name like Mia Müller, and this breaks it down to a token for M, a token for IA, a token for mu, and a token for lur. And they said, well, it's broken down, so this means it's not personally identifiable, and it's not sensitive data anymore. Now, of course, if you put the same token into GPT-4 plus, you get still the MIA as two separate tokens, but you get Müller as one token. And a lot of the other tokenization for German also changed. And you could try it with whatever languages or whatever common names you like, but lots of English common names are just one word. So like the word John, last I checked, is still one token. So what's happening here? A, why is there a difference between the tokenizers? And B, what does this mean about the learned relationships when we look at the embeddings? And then the learned things that we have in the neural network or the deep learning network from those relationships, right? Because these are all related. Take the token information, put it into embeddings, try to learn the relationships between the embeddings. And when we learn, we don't learn one token at a time, we learn many tokens in a row. So it's important to also think about the fact that when we see these in a sequence, we see them in a sequence. So the problem with the take that Hamburg had is not only is it a poor understanding of encodings, because these embeddings are just encoded information. If you give me the numbers that this represents, let's say this has an ID of 173 and this has an ID of 482, whatever it is, if we see these, I can go look them up. So AI can encode and decode. There is absolutely zero reason to think that M with the next token of IA cannot be rewritten as MIA, because that's the whole point. If it didn't rewrite properly, we wouldn't be able to do machine learning. It's like how your computer takes text and it turns it into bytes. You don't have to understand or read the bytes, but you can take the bytes and turn it back into text. Not only that, but what we can see is that the way that the encodings work has changed. And we could also understand that if the encodings change, also these relationships that are learned change, and these connections and density between the words change. And the whole point of us doing all of this work is to learn the actual relationships and represent them and learn them automatically via some sort of deep learning or AI model. And so not only is the take on tokenization incorrect because it misunderstands that tokens are just a form of encoding and that embeddings are just a form of encoding, but also the fact that the whole point of doing embeddings is to store more information, not less. And the whole point of using those for deep learning is to extract that information and to be able to store it into a model. And this is part of how memorization in machine learning also happens, which you will continue learning. So I hope this was interesting. You can read the full article and maybe you can start thinking, what complex data do we take and put into AI and ML systems? And what are we trying to learn from it? What might we memorize of those embeddings? And why might we need to memorize it? So if I want to take a generative AI system and I want to tell it to write me a poem in the style of E.E. Cummings, or if I want it to draw me art in the style of Monet, then I absolutely need to learn who those persons are and what they're related to. And I might not learn exactly who they are, but I certainly am going to try to extract the information between those concepts so that I can properly learn it. And this is really important to consider when we think about deep learning tasks and memorization. So, more next week.